L plus C. Alright, that's what we gotta do, but that's not adding them vectorially. Add them vectorially. Now, what we have here is x of L is always positive, x of C is negative. So when we add a negative, it's the same thing as subtract. Sometimes we just eliminate that positive or plus sign and subtract. Right. Same difference. Same difference. They're different and not the same. So you can either put a plus here, knowing that this is negative, or just go ahead and just make it minus. Either way, it works the same. Because once you get this difference, when you square it, that negative sign goes away anyway. So with this particular problem, we got square root of 100 squared plus 120. L is positive, plus a negative 40 or minus 40. Rest and C. That's going to be squared. That'll be square root of 100 squared plus 80. Want y'all that into your calculator?
28.062.
Get 100 squared plus 80 squared equals second function square root, second function answer, get 128. The impedance also has what? An angle associated with it. That angle is always the arc tangent. Tangent minus 1 of the reactive component. That's 80. Divided by the resistive component. That's 100. So we're looking at an arc tangent of 0.8. So if you go in your calculator, hit second function tangent, hit 0.8, you get 38.66 degrees. Impedance angle and the impedance magnitude. Now, the impedance having a positive angle tells you that most of the angle is due to the inductance and not the capacitance. Because we got more inductive reactance than we have capacitance. So the circuit is inductive. It's got a positive value for the inductance or a positive value for the reactance, which means it's inductive. Because inductive, we always give it a positive value. All right. Now, figure out the current. Simply using Ohm's law. I equals voltage divided by the impedance. That would be the same as figuring the current in a series circuit of resistors. We take the voltage, source voltage, and divide it by the total resistance of the circuit. Well, here we're doing the same thing. We're taking the source voltage and dividing it by the total impedance. Because the impedance is how those components combine to affect the current. We combine them by adding. So, I equals voltage. Now, voltage is always going to have a reference angle of 0. We got to have something to reference it against. We start with the voltage reference. We call that 0 angle. From there, everything is referenced to that voltage. The impedance angle is referenced to this voltage. Impedance angle is 128 value, and the angle is 38.66. Now, we divide in polar coordinates. We consider this polar because it has a magnitude and an angle. Magnitude and angle, magnitude and angle, that's polar coordinates. We divide polar coordinates, we divide the magnitude portion, 120 divided by 128, and we subtract the angles. So we wind up with I equals point something. 120 divided by 128 be 0.9375. And the angle we get by subtracting. 0 minus 38.66 gives us a negative 38.66. At that point, I would stop. Think about it for just 1 second. Does it make sense? This negative sign means that the current is lagging the voltage. In an inductive circuit, the current will always lag the voltage. So therefore, I'm pretty confident I must have done it right. All right. So the current is 0.9. 0.9375 at an angle of minus 38.66. Now, if I need to know the voltage across a resistor, it's simply the current through the resistor times the value of the resistance. So 100 ohms times 0.9375 gives me 93.75 volts across the resistor. Same thing's true for the inductor. Alright. Value of the inductance in ohms, or the inductor reactance, times the value of the inductive reactance. So 0.9375 times 120 gives me 112 and a half. Volts. Excuse me, not ohms. And the voltage across the capacitance is the same way. Current through the capacitor times the capacitive reactance in ohms. We got 40 ohms times 0.9375. 40 times .75 equals 37.5. Alright. So, 12.5 volts, 37.5 volts. Now, we go back to our DC circuits. Sum of the voltages across those components should add up to be what? You gotta add up to be the source voltage. If we add these algebraically, they do not equal. That's over 200, that's over 240 volts. That doesn't add up to be 120. The voltages are out of phase. We have to add them vectorially. Everything we do with AC circuits, we gotta add them, divide them, subtract them, multiply them vectorially. The voltage across resistor, 93.75 volts. The voltage across the resistor, inductor, is 112.5. The voltages between the inductor and the resistor are 90 degrees out of phase. 180 degrees out of phase with the inductive voltage is capacitive voltage. Put them up here. This would have a phase angle of 0, this would have a phase angle of 90, this would have a phase angle of -90. Always 90 degrees out of phase with the voltage across the resistor. So we can add these two up, get a resultant of 112.5 minus 37.5. That's 0, that's 5, that's 7. So the result here, adding these two together, is 75 volts. And this squared plus that squared will give me this one. That'll be deep source voltage. You take 93.75 and square it. I sure hope this works. 93.75 squared plus 37 plus 112.5 squared. Second function. Square root of 93.75 squared plus 112.5 squared equals 146. Screwed up somewhere.
You trying to see what the voltage? You got the voltage right?
Okay, 93.75. plus,
You got them right?
yeah, okay, I got subtract what I did.
Okay.
Parentheses, 112.5 minus 37.5, close parentheses. Equal 75. 97, there we go. 3.75 squared plus 75 squared equal second function. Root second function answer is 120. Yep. Alright. So when this come out to be 75, you square this, take the square root of this square plus that square, and it comes out to be 120. Tells you everything you did must have been correct. Alright, just a way of checking it. Now, power and watts. There's only one component that dissipates power. Only one. In that particular circuit. That's the resistor. Alright, so that's where we get power and watts from. Power and watts. Take I squared R, we can take B squared over R, or we can take B times I. I could care less which one you use. Whichever is most convenient is what I would do. Alright. You got the current, you can square the current, multiply by resistance. You got the voltage, you square the voltage, divide it by the resistance. You got the voltage, and you got the current, you can multiply those two together. Regardless of which way you choose,
106.
all three should give you the same answer. Alright. I take the current squared, 0.9375 squared. And then I multiply that by the resistance, which is 100 ohms. I get 87.89. Or if I take the voltage, which is 93.75, and I square the voltage, and then divide that by 100, I get 87.89. So that gives me the same answer. Or if I take the voltage, 93.75 times the current, which is 0.9375, I get 87.89. So either way you look at it, power watts is 87.89. Now, the volt amperes. Volt amperes we get from the source voltage and the source current. The source voltage is 128. Source current is the 0.975. So this would simply be source voltage, 120, times the source current, 0.9375. And you do that, that is the power that it appears that we're supplying from the battery or from the source. So we got 120 times 0.9375. Get 112.5. amperes. Alright. The volt ampere is reactive. That's the difference in these two powers. You can compute the two powers together separately and then subtract them, or and the reason you would subtract them because when this one is taking power, that one's providing power. When this one's providing power, that one's taking power. So they constantly, each half cycle, taking and giving. Take power and they give it back. We call that power lossless power. Right? So we can take,
source voltage.
we can take difference in the voltage here. Voltage was 75 volts. Alright. Times the current, 0.9375, gives us 70.31 PA. 70.31 volt amperes reactive. That was the difference in the voltage, 75 volts between these two components, times the current through the components. Now, from that, if you would like, you can construct a power triangle. You have the resistive power, power in watts, 87.89. You have the volt amperes reactive power. That was 70.31. And this power will be the volt amperes. Just to make sure this is all correct, square this power, square that power, take the square root of it, and get that. So the second function, square root of 87.89 squared plus 70.31 squared equals 112.55. What we calculate here, 112.5. Here I got 112.55. Alright. So these two did equal that, and you got a phase angle, theta here. Alright. Just so happens that that is the same angle as you get when you calculate the impedance. We wanted to know what this angle is from here, we take the tangent, arc tangent rather, of the tangent. Tangent is opposite over adjacent. So we want arc tangent of the tangent. So we want arc tangent of 70.31, the reactive component, divided by the resistive component. Right. So second function, tangent of 70.31 divided by 87.89 equals 38.66. Which is exactly what we got right here. All right. Now, the power factor is always the cosine of theta for a power triangle or for impedance times 100. I'll make sure we multiply by 100. That's power factor. Power factor in this case, I got 38.66, and I'm going to take the cosine of that. So cosine, I find the button, there we go. Cosine of 38.66 equals 78.78. 0.78 times 100 equals 78% power factor.
Jake, what is just a, capacitance? What is the current, the positive, like the angle, the positive instead of negative?
Alright.
Or
That's a
like
series
the,
RLC circuit.
impedance's angle would actually be negative if it was just.
If I did not have a C in it, we would do exactly the same thing, except that subtraction of the C doesn't exist, be zero. All I have to do is deal with this one reactive component. I still gotta square it, and to the resistor squared, take square root of the impedance, but that's all I gotta do. Any questions on that one? Picking out right, just picking backwards. Alright, now you have a parallel RLC circuit. Ask you the same questions. Total impedance, source current. Now, instead of V, why don't I ask V? About VR, why don't I ask about VR?
The voltage is the same across the board.
The voltage is the same and it is 120. So, asking you what the voltage across the resistor is,
You need to ask anyway so we get one right.
is simply the source voltage. Right. The voltage across the inductor, 120. Voltage across the capacitor is 120. But what I might be interested in is IR, IL, and IC. Also want to know power watts, power VA, power volt ampere reactive, and while we're at it, power factor. Start with impedance. Now, impedance here, I would use the 1 over method. If it were resistors, we'd be 1 over R1 plus 1 over R2 plus 1 over R3. We're gonna do the same thing here. 1 divided by 1 over R plus 1 over X of L plus 1 over X of C. Trouble is, that's not correct because that's algebraic addition. These are reactive components. This is an AC circuit. We got to add these all vectorially. We'll square that. We'll square that. And take the square root. That's exactly what we did with series circuit. We took the resistive component, we squared it. We took the difference between the reactive components and we squared them. Alright, and we took the square root. That gave us the impedance when we divided in the series circuit. Now we gotta divide into one to get the impedance in the parallel circuit. Alright, the fact that we got the one over here, the one over here, the one over here, makes it all work out correct. Alright. This impedance will also have an angle. Be the inverse tangent of the reactive component divided by the resistive component. So what we're looking for is the angle, which would be the reactive component, 1 over x of L minus 1 over x of C, divided by resistive component, which is 1 over R. And that will be the angle. Still reactive component divided by resistive component. All I gotta do is plug and chug here. Bless you. Alright, I'm just gonna put tangent minus 1 of 1 over 240 minus 1 over 80 divided by 1 over 200. Alright. All I'm doing is plugging information in. I got the equation. Now it's just a matter of plugging and chugging. Let the calculator do the work. So, take 1 divided by second function square root. I'll put 200 1 over x, square it. Plus, at this point, I put in parentheses. I put 200 1 over x minus 80 1 over x, close parentheses, square that, and hit enter. I got 110.94. And it's gonna have an angle. Alright. So I hit a second function tangent. And then I put parentheses, 240, hit the 1 over x button, minus 80, hit the 1 over x button, close parentheses, and divide that by 200. Hit the 1 over x button, hit enter, and you should get negative 59 degrees. Being that the impedance is negative, that tells us that the circuit is capacitive. Because what's going to happen, we divide this into the voltage to get the current, we're going to subtract the negative angle, which is going to give us a positive angle, which is current that is leading, which is capacitive. Alright, so let's go ahead and write this down. It's 110.94.
How did you get 110?
59 degree angle.
What you get?
Let me try this again, hold on.
For 240 multiple 200.
No. I got 102.899.
Oh, let's see.
I have it right. I know what I'm doing. Man, finally got it in this semester, but I know what I'm doing now.
I'm in the same boat.
102.
So you got 102.
Yeah, 102.89, blah, blah, blah.
I get 102.89.
See, I was about to say,
Oh, this is all my couch.
what you need?
Get the angle right.
Yes, sir. Yeah, you got that right.
Okay. Alright. At least they got something right. Alright, so T doesn't do this. Point nine, angle minus 59.
Don't put parentheses on. Looks good.
Alright. Now, if I want the current, I gotta divide it into source voltage. Source current equals the source voltage divided by the impedance. In this case, it'd be 120, angle 0, divided by the impedance of 102.9, angle minus 59. Source current will be 1 point something here. 120 divided by 102.9, 1.16. Or 1.17, however you want to look at it. And the angle is going to be positive 59 because we're going to 0 minus a minus 59 would be positive. Current is 1.17. It has a positive angle of 59, which means the current is leading. If you look over here, who has the most current? The lowest value. Most of the current is coming right here. What does that mean? It means it's capacitive. It means the current's going to be leading. Right? That's what we got for results. We got a leading current. All right. Now let's see what we got current-wise for each component. We got 120 volts across everything. This current will be 120 divided by 200. 120 over 200. That'll be the isolar. Right? So 120 divided by 200.6, I hope. 6 amps. We look at the inductor, it's in ohms, so we take 120, we divide it by 240, and we get 0.5 amps. And if we look at the capacitor, we got 120 volts divided by 80 ohms.
1.5.
We get 1.5 amps. Amps, I'm sorry. three currents add up to be the source current. Alright,
So
just to check,
3.9.
let's see if that's true.
Yeah.
Well, we can add the currents, but we have to add them vectorially. Alright, so we're gonna add the currents, just to check, see if we got it right. I source is equal to, alright, I sub R plus I sub L plus I sub C. Alright, but we cannot add those algebraically. We gotta square this one. We gotta square, these are 180 degrees out of phase, so we're gonna add these together and square those and take the square root. Alright, we just plug in information. I sub R is 0.6 squared. I sub L, 0.5 minus 1.5 squared. Or, actually, looking at currents, this current is negative, this is positive. Doesn't really matter, because you're gonna take the difference and square it anyway, it's gonna be positive when it's all said and done. And we're gonna take the square root of that. So you do that, this becomes a 1. Negative 0.5 plus 1.5 is 1. You square 1, you still get 1. Alright. You square 0.6, you get 0.36. 0.6 squared. 0.6 squared. 0.36.
I probably can't accept data that big, right?
Yeah, see.
Yeah.
Take the square root of that. Alright. So you get 1.36. You
Yeah.
take the square root of that.
Let's see. What are you gonna do? Whatever.
And you wind up with
Probably.
1.166 amps, which is what we got over here,
have a name for it?
1.17.
Jump hard.
Does that work?
So that's just a way of checking, or you could have found the current that way, it doesn't really matter.
I was thinking.
You could have found the current from each individual stage right off the bat. Here are the currents. Here are the currents. You don't want the current coming out of the source.
75, yeah.
Square this current. Subtract those two currents from each other, square them, and take the square root of that, and that gave me the 1.17 amps. Alright. Most of it went through the capacitor. What's always interesting, I guess I'll say interesting, is the current in the capacitor is more than the current that we're getting from the source. Alright. At first glance, you kind of think, well, that looks a little weird. What's happening is this current from the inductor
Is it like bouncing back and
is
forth?
supplying the current to the capacitor, and the other half cycle, the capacitor is supplying current for the inductor. They're not even looking at the source. This current over here is just sloshing back and forth. Once we got them started, these two are just supplying each other's current. And then the only current we got left is this current plus the difference between these two. Right? So that's the 1.16. Because we get, again, we gotta add them algebraically, we get 1.16 amps. Alright. I sub R in this case was 0.6. I sub L was 0.5. I sub C is 1.5. Again, just like the other circuit, power and watts. Ain't but one component up here that dissipates power. in watts. So, we got the voltage, 120, we got the current, 0.6, that gives us 72 watts. Power dissipated by the resistor. Alright, now we can look at the power dissipated by the inductor and the capacitor. And the difference between those two powers will be the power that is actually lost. Or power, not lost, but power that shows up as the volt amperes reactive. Alright, so we got 0.5 amps times 120 volts for the first one. Alright, it gives me 60 VA. Alright, volt amperes reactive inductive, VAR. The other one, 1.5 times 120 volts, gives me 180 volt amperes reactive. These cancel each other partially. We're gonna cancel out 60 VAR between these two. Alright. So that leaves me with 120 VAR. 180 minus 60. So VAR is 120 minus 6, 180 minus 60 is 120. The VA we already got. We just didn't know it. 120 times the current. 120 times 0.117. 14.
And 140.
140. 120 times. 120 times 1.17. 140. I need something. Now again, right now you might want to check that. Power in watts. 72 watts. Power volt amperes reactive. 120. And this will be volt amperes. Alright. If I square 7, if I take the square root of 72 squared plus 120 squared equals, I get 139.94 or 140. Which is exactly what we already calculated right here. And this also has an angle, right? And that angle is going to be 59 degrees. Now, it actually is negative because I should have drawn this way. So there was capacity and stuff, right? So the angle is actually negative. So it should look like this. That'd be minus 59 degrees. So if I take square that, even though that's negative, you square it, all it works out to be positive and everything comes out to be. The power factor will simply be the cosine of this angle. Or we can take power factor, we find the cosine of the angle simply by finding the angle, which would be the arc tangent of the 120 divided by 72. Alright, so 120 divided by 72 equals, that's the arc tangent of that, 59 degrees, and then take the cosine of that, and you get 0.51. So power factor, 0.51.
We're talking about how many?
59,
Smart.
cosine 59.51. So 51% power factor.
Last bit class now, man. Never mind. I was just jiving.
Alright, any questions on that one? Technically, you should draw the power triangle negative, but you get the same answers. Which way either which way you draw it, so I don't ever worry about going negative with it. I just know that the angle's negative from here, or from the impedance. We already figured that angle up here is minus.
Take a break.
We'll take a break, we'll do, if you decide to come back.